We are ready now to present part 2 of the rotor design discussion and techniques for asynchronous induction machines. This is lecture number 21, and I'm Jim Hendershot. Let's start with a summary of the list of the major design consideration. We have to decide first we're going to cast this rotor, fabricate it. We have to select the number of bars and rotor slots versus the number of stator slots. We have to select the cage material, aluminum or copper, and then most important, the bar shape itself and its location, the slot fit, whether it's skewed or not, and then of course the air gap between the rotor and the stator enters into this, of course. Next, we have to know what our speed torque requirements are, how we're going to operate this. We assume by definition of this whole series of lectures that these rotors are designed for inverter duty, not for fixed voltage and frequencies grid power. We mustn't forget about the thermal expansion issues, differences between the different materials, the steel laminations, aluminum bars or copper bars, and the end rings. And then we mustn't forget about the stresses, the mechanical stresses due to thermal and due to torsional torque effects. At some diameter, the end rings will need to be extended beyond the core length to allow for bending stresses on the copper bars to prevent shear stresses on the bars, etc. Otherwise, if there are shear stresses, they're going to fatigue and fail. I've noticed that some large machines, their rating is determined by the number of starts. These are grid motors, of course. Now this is a picture of a typical rotor punching designed for vector-controlled induction motor or inverter duty. Notice the teeth are parallel, the slots are tear-shaped, and the slot openings are semi-closed, and the teeth tips are not thin, they're quite thick. And the purpose of that is to set this angle of the tooth tips at approximately 45 degrees, and that gives a lot of strength in the throat here, so that if we can get these bars in there and get them restrained and get them tightened, then at higher speeds in the center of the rotor, the centrifugal force on the bars, which might cause them to bow or bend, they'll be hopefully restrained by these tooth tips. Lamination material, we talked about that at great length. Whatever applies to rotors applies to whatever applies to stators applies to rotors. Semi-processed steel with no core plate, or fully processed with core plate, and semi-processed with core plate and annealed after punching, as long as you use a core plate that doesn't burn off when you anneal it, and the C5 core plate does that. And as you can see here, the color of these indicates which one was which here. The darker one is C. That's semi-processed with anneal after punching. You can, after a while with experience, you can tell by looking at an existing lamp which one of these it is. Some machines, the larger machines, have keyways in the bore, and smaller machines don't. They just shrink them right on the shaft. We discussed the slinking construction before. This is a very excellent way to make a rotor. This actually shows an outside rotor machine, but the same process of whether it's inside or outside. You save a lot. You start with a strip of steel this wide, and with special dies you punch these teeth, and then you wrap it up and roll it up like a slinky toy. And they've even got this automated to the point where the spacing in the wrap and everything is such so that when you wrap this up, they're all aligned. The slots are aligned perfect. It's a beautiful process. It's expensive tooling, and it requires maintenance on the tooling, and it costs a lot of money to get ready for it. But it's an excellent way to make a stator at low cost. Now, we have to select the number of rotor bars. That's important, and there's lots of rules and guidelines for that. Most of them that have been critical have been single-phase machines that that can have resonance problems, get stuck and won't start with certain inertial loads. But with three-phase polyphase machines, that's not as big a problem, but there are some guidelines you have to go by. And one could say that the rotor bar numbers should be about 1.2 times the number of stator slots, or it could be 0.8 number of stator slots. Can never be the same. Now, the other thing is to adequately establish poles in the rotor that will generate sinusoidal voltages in the rotor. You need a certain number of bars. You can't really do it with one bar per pole. So a good rule of thumb is 5 to 7 rotor bars for each pole, at least minimum of that, and higher if possible. Larger machines, you want to go up to 7, 8, 9 rotor bars per pole. And it's a tricky balance with these machine designs to get the width of the bar and the width of the tooth optimized so there's no space wasted. But with the tooth, we've got to deal with low speed, peak torque flux densities. And you don't want to get to saturation or you're all finished. And in the case of the bar, you've got to, at those same peak torques, you're going to be at maximum current because to create the peak torque, remember the torque producing currents is flowing in the bars of the rotor, so to get peak torques you need a lot of current, so you've got to have your current densities at acceptable values as well. And some rotors are skewed, some aren't. Now here's a classical list that we've presented this before. Well, it's worthwhile including it in this lecture again for reference. This is a list of by Reliance, by Baldor. They're both owned by ABB now. And this is a list by horsepower of 2, 4, 6, 8 pole motors that these are the standard slot and bar combinations that they use, and the highlighting I think is shown on another slide. I didn't repeat it here. There's the super efficient ones, and then the normal. 3 levels of efficiency here is what those codes mean. But you can use various sanity checks for the number of rotor bars to slot. Tom Lippo writes in his famous book on induction motor design some things to keep in mind. These cusps he talks about in a torque speed curve due to MMF harmonics, those have to do with single phase machines, but here's some guidelines for the number of slots for stator versus rotor with respect to what makes them noisy or vibration. Here's a cogging relationship to avoid. And he gives his own list here in summary of the stator and rotor slot combinations by pole. Now I find this list very interesting because, and you can leave it to you to compare it with the Baldor's list on the previous slide, but here's the point about this. Lippo spent most of his career designing machines for use with inverters, so that's why I think this list is worth considering as viable. And we've already studied these in the last lecture series, all these different shapes and rotor bars, and here you certainly want to avoid anything like this, anything like this, anything like this. These aren't bad, but they're awful deep. This kind of configuration is the most suitable, I think, for inverter duty. The only thing you might do is use a few more bars per pole than what traditional designs have used, particularly if you increase the number of poles past 4. And we've studied that, the seeming restriction of 4-pole induction machines up to 1,000 foot-pounds. Here's a typical plot that's provided in a lot of the literature. You'll see various forms of this that shows the effects of the resistance of the bar rotor. Here's a case where the rotor has very low resistance, so the slip is low. That's good. That means the efficiency is high and power factor is high at rated rated performance up in this region here, but its starting torque is very low, and in some applications starting torque's not required. So if you're driving this with an inverter, you really want a higher starting torque. You want something like this, and you're willing to pay for a little loss in efficiency and power factor because your slip's going to be higher down where you're loading. Now here's a case of a machine with a very high resistance, very high starting torque, but terrible power factor and terrible slip to get the same load, you see. So the point is that these configurations of these configurations here are designed to give you a performance like that, or like that, you see, as we've seen in other slides. But for inverter duty, this is the only one you want. You want a machine like that because you're going to take care of this starting torque problem with the inverter. You take care of that very easily by controlling the magnetizing flux, which open loop run off the grid. The motor can't see control of its magnetizing flux. It's determined by the high slip. Whereas with the inverter control, you control the relationship between slip and voltage. So that problem goes away. Now here's a composite of all the, I think this includes all the known bar shapes that man's ever tried or done for a variety of different reasons, and I find this just amazing what a collection of bar shapes, and I don't think very many of those are useful for inverter duty. But there might be some of them you could use. My guess would be you might be able to use that one. I suppose you might be able to use this one and maybe these. I'm not sure, But there's no guarantees, and the best choice for you requires extensive analysis and even testing. But to get started, let me recommend to get started. To start with, use Type A, NEMA Type A, until you and that is this one here with nice teardrop shaped slots with parallel sided bars. That's where I would start until you develop your own optimization techniques and so on. So let's talk about some guidelines for adjustable speed drives, rotor bar designs for adjustable speed drives. That's what ADS stands for. You want to position the bars as close to the rotor OD to minimize leakage reactance. We don't have to worry about high resistance starting torque and none of that. We're going to take care of that with the inverters, I just said. Now the die-cast rotors can use semi-open slot and cast the conductors, fill the slot ovens right up to the OD, and you can even finish the OD. Take a cut in the OD after it's cast, after it's shrunk on the shaft. I think the tooth tip angles in your lamination design shouldn't be real thin. We don't want them to saturate, but on the other hand, we want them to be thick enough to provide some mechanical bar retention. Further than that, the bars have to be retained in the slots to prevent vibration on fabricated cores, it's seldom a problem with cast rotors. Swaging is used for bar retention, brazing in place for bar retention, and I believe that bars can be retained with vacuum applied high temperature adhesives. I think that's a very good way. Some of those adhesives even have excellent dampening characteristics. And I recommend the use of at least 6 bars per pole for 4-pole machines, and higher for larger machines and higher pole numbers. Increase the number of bars per pole with increasing power. Use FEA analysis to determine final bar selection and shape for max efficiency and power factor. I mean, you start with your best guesses, and then it's trial and error FEA analysis to predict what the right results, which you eventually have to validate with hardware. Anyway, here's some more guidelines. The adjustable speed drives are going to use either constant volts to hertz control or flux vector DEQ axis control. And the most dramatic improvements, inverter fed Induction machines is achieved by optimizing the rotor slot and the bar quality, shape, and the bar material itself, going from aluminum to copper. Inverter-fed induction motor starting conditions are soft as compared to grid-powered motors, as I've indicated before. This results in much smaller radial loading forces on the bars during startup and acceleration. However, the bars must be tight in the slots and not prevented to vibrate. Here I repeat the rotor bar frequency again, which was in the last tutorial. This vibration is caused by high current forces on the bars. If the bars are loose, they will work hard in overtime and break. And these vibration forces caused by high current forces, those are caused during startup of a grid-powered machine. For example, I don't know if I state this elsewhere or not, but those starting currents can be 650% of the rated currents. So that causes tremendous forces on those bars, torsional and inertia forces on the end rings, and with an inverter driving the same machine, the starting currents are only like 150% of rated, 200%, 300 at the most. But even that can be ramped. In addition, these thermal stresses in the bars due to the temperature variations within each bar from top to bottom of the bar. Here's an example. Here's a published example I found of a grid motor that they measure 250 degrees C in the bar close to the slot opening, 25 degrees C in the bottom of the slot, and the gradient extended to 100 degrees C in the center of the bar. That's a tremendous gradient of temperature from the top of the bar to the, in the length of the bar. These kinds of thermal stresses aren't near as severe with an inverter driven machine. We can happily conclude that because of the ability to control the frequency and the voltage and the magnetizing current. Here's where I state that the grid-powered machines see rotor bar starting currents high 650% of rated current versus 150% of rated current for inverter-driven machines. During grid starting from zero speed, this starting current flow is in the upper part of the bar close to the rotor OD due to the skin effect of the current penetration. As the motor increases speed, the bar currents distributed down into the lower part of the bar, and the frequencies, because the frequencies seen by the bar decreases as it goes faster. But this is typical of the control with an inverter. This means that the life of the bars is based on the number of motor starts when powered by fixed voltage and frequency from the grid, which shouldn't be a limitation with inverter duty. The starting situation is not such an issue with inverter-fed machines because the skin effect is mitigated because of the continuous control of voltage and frequency. The skin effect's not a factor either anymore because the bars are never exposed to high frequencies causing high slip during startup. Here's some rotor bar choices for these fabricated machines. You can use aluminum with hard anodized coating, aluminum with no surface coating, aluminum with light anodized coating, and copper without anodized coating. These can be extruded or rolled. The rotor cooling issues are quite serious because of the ohmic losses in the rotor. They produce very low iron losses due to the low slip, at least inverter duty motors, because you're controlling the slip at all times. So the iron losses are less in an inverter duty motor than a grid motor that is subjected to many starts and stops. But the inverter duty motors do produce significant heating from ohmic losses because you have a tendency to utilize the motor at higher currents at lower speeds, because you can control the magnetizing flux. So that means you're, on average, through the use of the motor, you're going to put more current in the motor more of the time, more in the rotor. And since there's only one turn per phase, the current in the rotor is pretty high. The entire rotor is mounted in bearings, and that's the only contact from the source of the heat of the rotor is through air around the rotor, of course, but the other thing is through the contact of the balls to the races to the shaft to the so the diffusion pass for the heat sources is not a happy one, and it's long. Uh, but it's still tempting to use an existing lamination because it's cheap and it's available, even though the tooth of the rotor and the tooth shape and the slot area were not optimized for use with IM applications because of this current. So you want to start with the NEMA Type A. That's your best bet if this is the case. Don't try the other ones. Either what happens with the wrong slot area is either current density is too high or the tooth flux density is too high for the peak torques. Either way, the machine is going to be limited by the rotor heating. And if the current density is excessive, and a good number to think about is shoot for continuous 5 to 6 amps per square millimeter, or a little higher maybe. You can run the peaks higher than that, but not continuous, unless you have some serious cooling. And it seems that for induction motors to compete with permanent magnet machines, you have to use serious cooling. Small die-cast aluminum machines have crude fan blades cast into the cage, not very efficient, and they circulate cooling air, but that benefits both the rotor and the stator, and it still adds a lot to the continuous power rating. But special cooling systems utilizing the cage to focus circulating outside forced air cooling, such as air inlet deflectors around the shaft. I think we have a picture of that in slide 217. The numbers didn't change since I made this slide. The cooling vents are fabricated into the rotor cores to improve direct air cooling and shorten the thermal diffusion paths. Those are those cooling vents in the stator and the rotor that I've showed you many times. The most effective method to cool an induction motor is through the use of an external blower ducted into the machine to cool the rotor and the stator. That's an external motor mounted on a totally enclosed motor with an inlet and an outlet, but this is a loss. There's no question about it. It's a double loss. It's a loss in the machine that's creating the heat that has to be cooled. Then the further loss to the grid is the power it takes to drive the blower to cool the motor. So the other way is the other very just as effective way, if not more effective, is liquid cooling of the rotor and spray coating and things like that. We'll study that in a later lecture, but that has its whole set of problems too. But high performance machines for vehicle traction will use splash or spray coating directly on the rotor and the end rings. Here's a example of a machine that has a fan mounted on it to take air that's sucked into the end frame and properly deflected. Here's another example of a inlet air deflector that's mounted to the shaft, on the shaft in front of the rotor, so that when this fan causes the fan at the end of the rotor, and it could be shaft mounted or cast part of the end, will create a vacuum here. A vacuum is created under here because this is a centrifugal fan, so a vacuum will be created here. So with an air deflector like this, that causes air to be sucked in this deflector. Without the deflector, it would be sucked out here. But with this deflector, and if I have a finned frame, end frame, like we saw in the last slide, that will cause outside air to be sucked into there and sent out here. There has to be a place for that to go, of course. And then, of course, this deflector also, if there's holes in the lambs here, this allows that there's a vacuum created here as this spins too. So the air deflector allows air to be sucked in through these passages and cool. In that manner, there's a very effective way. The forces on a rotor, here's a summary of all the forces on a rotor. that's kind of an interesting summary that's worth analysis and study by your mechanical engineer counterparts. Final comments on rotor design. The leakage reactance is made of the sum of the following: a rotor differential, rotor end leakage, and current skin affection of rotor bars. These calculations are going to be approximated by using Professor Bolday's methods. FEA methods, although not faster, result in more accurate performance predictions due to the difficulty of calculating leakage reactance. If output torque versus current is too low, assuming the machine is, you have to assume the machine is large enough, the rotor leakage reactance is too high, so rotor slot shaping and radial location of the bars must be improved, and you might have to even improve the stator slot modifications. The rotor tooth versus the slot width must be balanced for current to produce peak torque and enough flux to produce enough not excessive flux density in the tooth part to produce the torque. So if the rotor resistance is too low, increase the slot and the bar width. Use thick end rings is good practice for inverter powered IMs. I'll pose a question why, but I said so later before that. Now there's a phenomenon that that exists in rotors. There's a cross-path resistance that develops in rotors at higher frequencies. Inverter-fed machines operating at higher speeds produce cross-path resistances in trapezoidal-shaped bars, which are the bars we want to use anyway. This probably is a problem at 500 hertz and higher. So these extra rotor losses caused by these cross-path resistances because the bars are uninsulated from the core, and there's really no way to insulate them from the core, so you're stuck with this, and this leads to stray load losses. A further discussion and analysis of this beyond the scope of these lectures, even though parallel teeth permit the best bar shape, it gives us these trapezoidal shaped bars. But there are several IEEE articles on these studies for your reference. Here's one of them, IEEE number there. You can look that up. The title is The Effect on Cross-Path Resistance between Adjacent Rotor Bars on Performance of Inverter-Fed High-Speed Induction Machines. Included in this paper is a formula for the affected rotor bar height versus frequency. And it's given by this formula and the legend there. So leave that for your reference and your own analysis. And I believe that concludes this lecture.